Hello, welcome back. Last time we learned what linear equations are, and we discussed how to solve them by row reduction. And in this video, we'll start discussing some finer points of this technique and discuss other ways to conceptualize systems of linear equations. So echelon, so it's a French word, hence the pronunciation, and originally meant a diagonally military formation. So like either soldiers, like troops during the movement of the troops, or here fighter jets. And of course, the idea used in many other places in civil applications, right? So here, this peloton of bicycles during the race, right? It's maybe Tour de France. So they formed in such a way so that the wind that is blown from this direction, so other cyclists are shielded by their friends from their teammates from the wind which blows in this direction. So this formation has been since antiquity, and it offers a lot of convenience in various aspects. For example, reduces drag in airplanes, birds, and cyclists, as it's shown here. So this shape will be sort of you'll see when we do the matrices, you kind of see why the method is has its name. So a matrix in echelon form is such a matrix when every non-zero entry for every row other than the first one, and so because is strictly to the right of a non-zero entry in the row above. So the first one, there's nothing above the first row, so you're just looking at the it can start from any position. So here, a square, the box means a non-zero entry, and a star means an entry, zero or not. Okay, but what's important that there are all zeros underneath it. And a reduced echelon form is when the first non-zero entry of every row is 1, and every other entry in its column is 0, as shown here. Right, so what those squares have been replaced by ones, and then above those ones there are zeros. Here's the comparison between echelon form on top and reduced echelon form on the bottom. So let's talk about row reduction algorithm and see how those echelon form matrices can be produced. So first we choose a non-zero entry in the leftmost non-zero column. Then we bring it to the top row by exchanging rows if necessary. So remember, we can freely interchange the rows, and that corresponds to just renaming the equations, so moving them in a different place. So this entry is now set to be in a pivot position. Then we divide the row by the value of that pivot and add multiples of this row to other rows, including so-called covered rows, to zero out entries in the pivot column. Then we cover up this row and all rows above it and repeat the procedure on the remaining matrix. So let's do an example. So this is an augmented matrix of a system of 4 equations with 5 unknowns, right? We choose the non-zero entry in the leftmost non-zero column, which is this one here, right? So that will be our pivot. Here's the matrix, the pivot position. Then we bring it to the top by row exchanging. Well, in this case, it's we'll do this. We're just going to swap first and second rows. Right now, I have this matrix. Okay, and yeah, so this entry now is set to be in a pivot position. So when it's so this is our pivot, right? It's the first non-zero entry in this row. Here we go. And we add multiples of this row to other rows, including, well, here there are no covered rows, but we just add. So here we just multiply it by a -1 and add to the third row and by -2 and add to the last row. That's what happens after this procedure, right? So there are no all zeros beneath this one. All entries are zeros. Okay, so next step. So now we're going to cover this row, right? So we're not going to work with this anymore, or at least for now, for the time being, but we'll come back to this later. And then we'll repeat the procedure on the remaining matrix, right? So here we have 3 more rows, and then there's a choice, right? So yes, now the first row will color in green, meaning that's saying that it's covered, right? So we're not going to work with this for the time being. Okay, that's the starting point. Now we choose a non-zero entry in the leftmost non-zero column in the remaining 3 rows. So let's pick this one because it's convenient to work with, right? So we don't need to divide by anything. So we pick the 3rd row. Okay, so here you can swap 3rd row and 2nd row. So this one will be on top. And then we'll do the same procedure. Then we'll multiply the 2nd row by multiply it by -4 and add it to the 3rd row, and multiply it by -2 and add it to the 3rd row. So yeah, so this is our new pivot. And then we'll do this procedure that I just said. So it's the 2nd pivot position. So we can get rid of these 2 numbers, and that's the new matrix that we had. And then also we add, so when we also multiply it by -3 and add it to the 1st row. So see here that the entries in the 1st row got changed, right? Because we did this addition, but because everything from the left of this one was 0, nothing changed here. So we still have 0, 1, and then the rest was altered, right? And notice that there's in this 3rd column, there's only one non-zero element 1 here, which is in this 2nd pivot position. Okay, so that's step 2. And then we need to do this one more time, right? So we're going to cover up this row and then work with the rows beneath it. So these are covered rows. Okay, and you can see that the remaining system of equations looks pretty simple, right? We choose a non-zero entry in the leftmost non-zero column. So it's either these is either 2 or 3. So say we pick it that it's 2, right? This one. Then we divide by 2. So it's going to be like this. 1, 0, 0, 0, 1, 0, 1, the 3rd row. And then we multiply it by -3 and add it to the last row. And also to the 1st row. So we multiply by -3, add it to the last row, and then also to the first 2, right? So multiply it by -2, add it to the 2nd, multiply it just add it to the 1st one. So this is what we're going to get. Pause if you need to make sure to check the calculation. So let's talk about the uniqueness of the output. We have made choices in this algorithm, but the resulting reduced echelon matrix will always be the same, right? So we could have chosen, so for example, in the last step, instead of choosing this as a pivot, we could have chosen the other one, right? So we could have taken the 3rd row, we could have swapped it with the 4th row, we could have swapped it with the 3rd one, and then divided by 3 and did the same procedure, as well as doing things with other rows. But as you can see, it doesn't matter, right? Because the result would be the same eventually. So the algorithm is not unique, but the resulting reduced echelon matrix will always be unique. Now, but if we had not bothered dividing through on 0 or zero out entries above pivots, so instead of doing the reduced echelon form, we would be doing just echelon form, unreduced. Then the matrix will not be uniquely defined, right? But the shape will still be the same, right? So in the sense that echelon formation, of the fighter jets or the cyclists, the shape of this staircase would be the same. And the shape can be encoded by the location of the pivot entries. Okay, so try it yourself. So consider this matrix, right? And think about it, whether it's in echelon form already. So has it been reduced to an echelon form? What do you think? Pause for a second before continuing. It is, right? So it satisfies all the conditions. So it's in the echelon form, but it's not in reduced echelon form, right? Because above this one, we have non-zero elements. So we can get rid of this 1, 2, and 3 here by using the last row for subtraction. So yeah, it is echelon form, but it's not in reduced echelon form. Where are the pivots? Right, so you would, so those are pivots over here, right? It's kind of, it's the shape of the matrix, the shape of the echelon formation would be this. Okay, how about this matrix? Is it in echelon form? Well, no, right? Because it's not how the echelon form looks like. Is it in a reduced echelon form? So of course, also no, because, well, if it's sort of reduced echelon form is a stronger requirement, right, than the echelon form. So where are the pivots? So the first row, it could be anyone here. So to do that, you need to produce the row reduction. So for convenience, let's swap the rows and then, well, multiply the first row by -2 and add it to the second one. So we have, so this will be one pivot, this will be another pivot. Okay. Good. So now let's do the so sort of next part of the story is the use this to solve the systems of linear equations. So here we reduced matrices. We showed how to reduce matrices to echelon forms and reduced echelon forms. And now sort of the second part of the algorithm will tell us how to find the solutions of a system of linear equations using the augmented matrix in echelon form. So what we just see in the previous portion of the video is that a series of transformations shows you simpler but equivalent systems of equations. So how shall we extract the solutions from this form? How do we read off the answer? So suppose we have a linear system whose augmented matrix is already in reduced echelon form. After all, we just discussed how to do that, like this one, right? So there are pivots here, here, and there, right? And then there are 3 pivot columns. Yeah, so perhaps we arrive to this system of equations by row reduction. So first we need to look at rows like this, which this matrix does not have, right? But it might. So if you remember the correspondence between the augmented matrix and the system of equations, it means that the coefficients which multiply the variables, so x1, x2, x3, x4, and x5, in this case are 0, right? So it means that this translates into equation 0 equals 1. And this system is inconsistent if you find such a row. So, and at that point, it's a done deal. It's a no-go. So if this row exists, a row like this exists, then the system has no solutions. Instead of 1, you can put any number, right? So if it's not 0, then the system is inconsistent. But in our case, there are no such rows. So we can proceed. It is a consistent system. So we now introduce 3 parameters for every variable whose corresponding column has no pivot, right? Where there is no 1. So here, so this column has no pivot and this column has no pivot. And let's call those 3 parameters S and T instead of X1 and X5, right? Just for simplicity. Now we need to express the pivot variables in terms of those parameters and constants. It will be the next step. So in this case, this matrix, since X1 is equal to S and X5 is equal to T, the remaining equations say that X2 here, right? So is equal to so T is this one, so it's X2 plus T equals 3, which means that X2 is equal to 3 minus T, X3 is equal to 2 minus T, and X4 is equal to 1. Right, so X4 is determined uniquely. And you can write this space of solutions as this vector, right? As this tuple of variables S, 3 minus T, 2 minus T, 1 and T, for any values S and T, right? They can be complex. They can be real, depending on which set of numbers you are working on. Okay. So number of solutions, it all concerns the number of pivot columns. So for a system with reduced echelon augmented matrix, there are no solutions if and only if there's a pivot in the last column. So that's meant in the augmented matrix. In other words, if the row like this exists, right? So if after you've done reduced echelon form and there's a pivot in the last column, it means that the last equation is inconsistent, which makes the whole system of equations inconsistent. Now, the system of equations has exactly one solution if and only if there are no pivots in the last column. So it's either or, right? So, and there's a pivot in every other column. So then it has exactly one solution, meaning that the system looks like this, right? So the right, so here, well, for example, the last row may not exist, right? So you can have something like, you can, if you like, you can cut the last, or this is also an example, but another example will be if you cut the last row. So here, basically, it tells us that this X1 is equal to this number, X2 is equal to that number, X3 is equal to that number. And the solution is unique. Okay, and then the third example, so remember we talked in the previous video that the systems of linear equations has either 0 solutions, 1, or infinitely many. And then finally, the system with reduced echelon augmented matrix has infinitely many solutions if and only if there are no pivots in the last column and no pivots in at least in one other column. So which means that there are 3 parameters. So in this matrix over here, we have 3 pivot columns, first, third, and fourth, but second and fifth do not have pivots, right? So therefore, in order to express the solution, we should introduce 2 free parameters for the say for X2 and for X5, and then express other 3 variables in terms of coefficients and these parameters, as we did in the previous example. So in this case, there's a 2-parametric space of solutions for the system of equations. Okay. And our final story for this video is vectors. So we're going towards geometric understanding, geometric meaning of the space of solutions of systems of linear equations. And let's talk about vectors. A column vector is a matrix with just one column. So here are vectors, right? So 1, 1, 2, 1, 2, 3, 1, 2, 3, 4, etc. So we write R in this font to the n for the set of column vectors with n rows. Right, so it's a space. It's the Cartesian product of space of the set of real numbers n times. Right, so instead of every vector, every entry, you can plug in a real valued number. So let's talk about real valued vectors for now. So in the above vectors, take values in R squared, R cubed, R to the fourth, etc. Now, vectors can be added with each other, and we do it term by term, right? So it's very convenient to do using those lists. So ABC vector ABC plus vector XYZ is equal to the vector A plus X, B plus Y, C plus Z, right? So it's very straightforward. And then obviously this only makes sense for vectors of equal size, right? So if they have equal number of entries, it's only defined in this case. Try it yourself. Add these vectors. How much is 1, 2 plus 2, 3? I'll take a moment. So it's 1 plus 2 is 3, 2 plus 3 is 5, so it's a vector 3, 5. Next, we have 2 vectors with 3 components, 1, 3, 2, 2, 1, 4. Pause if you need a moment. And the answer is equal to 3, 4, 6. Finally, how about this one? Well, those vectors are not the same size, so the addition is not well defined. Now, another operation on vectors is multiplication by scalars. So in order to multiply a vector by a constant, we multiply each entry. So a constant c, which is also a real number, multiplied by a vector with components x, y, and z is equal to a vector with components cx, cy, and cz. Yeah, so this constants also called scalars, as opposed to vectors, which are ordered lists of numbers. So you can say that they scale vectors. The word scalar means that they scale or change in magnitude, right? So they either expand or squish or extend the values of the vectors. Okay, well, another quick exercise. Multiply the vector by a scalar. So 3 multiplied by vector with components 1 and 2 is equal to 3, 6, vector with component 3, 6. 11 multiplied by vector with components 1, 3, and 2 is 11, 33, 22. Now, how about this? Can we multiply vector with components 1, 3 by vector with three other components? Well, no, because none of them is a scalar, right? So we'll talk about vector multiplication later, but it's defined for in a very special case, which is not, and this is not one of them. Okay, so we will use the boldface characters, boldface letters to denote vectors. So there's a bold V with components V1, V2, V3, V4. So it's very easy to type in LaTeX, and it's sort of nice to distinguish from the components of the vector. So vector addition, scalar multiplication satisfy the usual commutative, associative, and distributive properties just because the same is true for every entry. So you should think of a vector as just a list of numbers with order. So it's ordered tuple of numbers. You cannot swap them around. And these are the rules. So commutativity, V plus W equals to W plus V. So it doesn't matter in which order you add the vectors. Then this is the associativity for addition, right? So U plus V plus W is equal to U plus V plus W. So first you add these vectors and then add u to them. And second, you had u and v and add w to them. Then c multiplied by v plus w is equal to cv plus cw. So c is a scalar. And c plus d times v is the same as c times v plus d times v. Let us visualize those vectors geometrically. So it can be thought of an arrow like this, right? So for convenience, let's consider two vectors with two components. So vector A has components 2, 5. I just wrote them in a row here for convenience. So sometimes we'll be using row notation, sometimes we'll be using column notation. So you put the tail of the vector in the origin of the coordinate system, and the tip of the vector of this arrow will be at the point in this Cartesian coordinate system with the set components. So this is vector 2, 5. This is vector 5, -5, and this is vector with components -4, -3. So this works in for any Rn, right? So you can draw, of course, in R, R2, R3, but you can visualize this what happens in higher dimensions. Only there, you just would you wouldn't be able to draw the whole thing. Yeah. So if your imagination is strong enough, you can try. So addition geometrically looks like this, right? So you take vector A with components A1 and A2. Again, we are specializing for the two-dimensional case. For simplicity, vector B in green has components B1 and B2. We add them together, we had vector A plus B with components A1 plus B1, A2 plus B2. And then just from this picture, you can see that geometrically, it means that the sum of two vectors can be understood as the vector that goes along the side of a triangle, right? So the where two other sides are vector A and vector B. So you put the tail of vector B, put it on the tip of vector A, and then the addition law tells you that the sum of these two vectors will be the vector that has a tail which coincides with the tail of vector A and the tip that coincides with the tip of the vector B. So there is you can either call it a triangle rule, or you can also call it a parallelogram rule, right? So if you draw another vector A over here, and the sum of two vectors goes along the diagonal of a parallelogram. If you think about R1, then you have just vectors that are aligned along the same direction, and then you would just add or subtract their magnitudes. What's scalar multiplication geometrically? What, as the name suggests, it would scale the vector by some factor. So we keep the direction of the arrow, but we change its length. So for instance, 2v, or equals to v plus v, is a vector in the same direction as v, but twice as long. Yeah, or 1.8v, let's say -5v is the vector that goes in the same direction. So yeah, the positive numbers scale the vector and they keep the direction, but the negative numbers would you need to flip the direction. So say this is vector v, and then this would be, -0.4 v. The sign, whenever we have a negative sign, it flips the direction of the vector. Next topic is linear combinations and linear span. Definition: given a collection of vectors v1 through vn in Rn, and scalars a1 through an in R, an expression of this form, a1v1 plus etc. a2v2 plus and so on an vn is said to be a linear combination of these vectors, or linear combination of these vectors with coefficients a1 through an. And this set of all such expressions of all such linear combinations is called the linear span of vectors vi, or of all vectors v1 through vn. Example, so the linear span of vectors 1, 0, 0, 0, 1, 0 is the set of all vectors of the form where the first component is a, the second component is b. Right, so you can multiply first vector by a, second vector by b, and add them together for any values of a and b. Okay, so what's the linear span of vector 1, 2? What do you think? Well, it's all vectors when you multiply this vector by a number, right? So it's vector with components t and 2t, where t is any real number. What's the linear span of 1, 2, and 3, 4? So probably you can say, I mean, you can start with this, right? You can say multiply the first vector by parameter t, by constant t, coefficient t, the second vector by coefficient s, and then say that you get vectors of form t plus 3s and 2t plus 4s. And in some sense it's correct, but we can say more, right? So the answer is actually all of R2, right? Because so these are two independent parameters you can relabel. You can say that A is equal to t plus 3s and B is equal to 2t plus 4s. Okay, now next, okay, let's sort of ask a different question. Is vector with components 2, 3, and 5 in the linear span of vectors 1, 1, 2 and 1, 3, 7? How shall we check that? Well, let's reformulate this. So if it is, then there exists a linear combination of these two vectors with coefficients x and y such that it is equal to 2, 3, 5. Okay. So do y, x, and y exist such that this is true? And we know how to answer this question, right? So if it does, then the linear systems of linear equation with the following augmented matrix should have a solution, right? So if it does, then it's inside the span. This vector is inside the span. If it doesn't, then the answer is negative. So we can do little row reduction. We know how to do that by now. So in the first step, we get rid of entries in the second and third columns. And then we see that the bottom two lines say that 2y is equal to 1, and then 5y is equal to 1. That's what these equations tell you. Those two equations are obviously inconsistent, so there is no solution. So the answer is negative. This vector is not in the span of vectors 1, 1, 2 and 1, 3, 7. Okay. Now, let's talk about linear combinations in connections with linear systems more systematically. So take two equations with three unknowns, x, y, and z. Now, we can write this system of equations in a vector as a vector equation. So here, it means that we multiply x by the first vector, y by the second vector, and z by the third vector. And it's equal to vector with components 2, 6, and 3. So you can sort of reformulate this, the existence of solutions of the systems of linear equations by asking this question: does a linear combination of variables x, y, and z, does the linear combination of these three vectors exist, which is equal to the right-hand side? So in other words, finding all solutions to the system of equations, is the same as finding all ways to express vector with components 2, 6, and -3 as linear combinations of the said vectors. If you like, it's sort of the geometric meaning of existence of solutions of systems of linear equations. Okay, so that's it for this video. And I'll see you later in the, I'll see you in the next video.